Hi, everyone. Welcome to our third episode in our webinar series on reducing the environmental impact of roads through planning and design. My name is Erin. I've been your host through the series, and I'm excited to continue today. So today's episode really is going to focus on kind of more of the ground level stuff. We're going to be talking about geometric road design, specifically key factors in cross-section geometry, materials, and movement of materials that you should consider to help you reduce the impact of the roads you design. So if you recall in our last episode, we really were looking at it from 30,000 feet. So today's episode is all about, yes, much closer to the ground. We're going to be talking about cut and fill slopes, surfacing materials, spoil and borrow sites, and more. This webinar will also follow a very similar format to our previous episodes. So we're going to be moving back and forth between the theoretical content and then the translation of that theoretical content into actionable steps that you can take using a geometric design software. Now, of course, we're going to be showing you using Softree's geometric design software RoadEng, but a lot of the steps, again, can be applied no matter what geometric design software that you use. Trying to keep this introduction relatively brief, I would like to again sort of introduce our fantastic team of presenters. So first we have Jeremy Araki. As previously introduced, he is a wealth of knowledge on this topic. He's been practicing professionally for decades. He's been involved in shaping a lot of the professional policy here in British Columbia, and he's one of the founding members of On-Site Engineering. Now, if you're not familiar with them, On-Site is a BC-based engineering firm that practices throughout Western and Northwestern Canada. They've got a broad range of innovative and operationally realistic engineering and geotechnical solutions for across multiple industries, as well as for both industrial and for government clients. And I cannot stress this enough, how appreciative we are at Softree of the energy and the enthusiasm that Jeremy and his team at On-Site have shown for the webinar series, and more importantly, for the topic of reducing the impact on the environment. If you're interested in learning a little bit more about On-Site or getting in touch with Jeremy, there is a link in that resources handout, and you're welcome to check it out. Next is Matthew Dickey. I've given him a formal intro before, so today I'm just going to tell you that he's one of our software and engineering wizards from our Softree team. And if you're not too familiar with us, we're a civil engineering software developer. We're based in North Vancouver, and like pretty much all of you on this webinar, we love fresh air. We like streams that are full of fish, clean drinking water, and our goal in this series really is to help anyone and everyone improve their road design and reduce their impact on the environment. And then the last presenter, which is more of a contributor today, is Brian Chow, and he has really helped to shape all of the content throughout this series in a contributor role. And similar to our other presenters, Brian has a keen interest in promoting the knowledge and improving resource road engineering practices. So thank you to the three of you for being here today. And with that, enough of my introduction. I'm going to pass it over to Jeremy.
Thanks, Erin. And hello all again. Thanks for those who are tuning in for a third time. As you know, and Erin just said, we kind of spoke at a broad level of all of the background information around roads and planning and design and kind of how that ties into reducing environmental impacts. And so what we want to do with this is just kind of build on those concepts and talk about the details of the design. And of course, now that we have that adequate planning and background knowledge, we've set you up for success in the process, but the design stage puts all of those things to work. So, and this is where you can kind of set a balance of all the factors that you have to consider, and that's where these things get decided. And that, of course, includes the environmental impacts. So, kind of the details that we're going to go through today in how they impact the actual geometry of the road. Like I said, we've spoken about them, but we're going to talk about how they actually impact the road, as the materials and the properties of those, how that affects cross-section geometry, and then kind of the decisions around alignment, and then starting to think about the materials that we're excavating and how we're excavating and where they're going to. And of course, all of those things, as we talked about before, they're going to impact water and sediment. And so those concepts that we've been bringing through before, there are a lot of impacts in the environment from roads, but water is one of those main contributors. So as before, you'll see that theme kind of going throughout the rest of these. So why do we do benefit? Why do we do geometric road design? Well, we talked about that circle of life of the road before: planning, design, construction, maintenance, use, and decommissioning. And that the geometric road design is the visual representation through time of this process to everybody involved. And that's kind of the key thing to remember as we talk about how we model this and how we're gonna portray it. Because of course, you can do all the planning in the world, but if we're not communicating it or showing what needs to happen, or getting it to a place where we can understand some of those ancillary impacts, all that planning is for naught. And some of those impacts are, like we said before, are well outside your main objectives, but still important in the process. And of course, the design itself, it references what's in the field, and it connects the actual ground conditions. So in that, how would we reduce environmental impacts through road design? Well, through all of the things that we just spoke about, and understanding how they impact the environment and the magnitude. And so again, the same things, their materials, what your road is going to look like, where your road is and the shape of your road, and how much material you're moving in and out. And we'll get into the details of that as we go through. But everything that we're doing here, we're it's obviously reality based on how you're actually going to do this, but it's got to tie back to what those impacts could actually be. So we're thinking about that stuff, maybe not even in the background, but it's sitting on our plate of things to consider. So as we get into the details here, I think it's important we just talk a little bit about the basics of road geometry. I'm sure you're all familiar, but it's worth going through. And we'll get into each one of these pieces in the next hour here. But obviously the cut is the material that you're excavating out of the bank on the top of the road. The fill is where the material that you're placing in the bottom. That fill has a fill slope that it can stand at, and the cut has slopes that you'll cut at, and that differs by material. Of course, in most cases we have a ditch, we have some surfacing on top, and then the subgrade that's holding that road up. So that's just broadly reminding us of the pieces of the road. So what's the most important thing when we're thinking about how we're going to build a road? Well, it's the soil. It's the soil or the rock. It's what we're actually building in, and we need to understand those soil and bedrock properties, because they're going to impact things like your cross-section geometry, the footprint of your road, the erosion potential, mass haul, the movement of materials, and the lifespan or the maintenance required over the lifespan of the road, and even things like control points, like where do we want to avoid, where do we want to be, and of course all of those things tie back to cost. And again, as we spoke about before, the more planning you do, the more time you have to consider all of these aspects, and that will impact your cost, because the more you can plan and understand, the more you can avoid things, get to things, make sure there's time for everything. And of course, on the soil side, this topic is the basis of full careers and lifetimes of study. Here, all we're trying to do is get a basic understanding of how it impacts our project, and that's in soil, its strength, what it's doing in situ or before you touch it versus once you touch it. Sometimes it has cohesive properties, its permeability, what's drainage doing, and moisture content, how much water is actually there. Same thing in bedrock, how strong it is, which is generally related to the type, but also in that type, the jointing or bedding, how it's weathered, and then what happens when you cut it. Are you releasing MLARD is metal leaching or acid rock drainage? So we're thinking about all of those things and how they're going to impact a road or what role they're playing. So for example, if you have a colluvium apron, like an old gravity deposited feature, and it's poorly graded or gap graded, and there's no small material to bind that large material together. If you cut it, maybe you can't cut it very steep, 1.5 to 1, 2 to 1. Whereas if that material is well graded, you can maybe cut it steeper if it's placed by a different process. Or if you have a silty sand that was placed by a fluvial deposit, and after you excavate and compact, you may shrink that material, or it may behave differently as you're cutting it. You have that same exact material, the silty sand, that was part of a till that had several kilometers of ice on it, and that's going to cut differently, and it's going to probably expand when you cut it. We'll talk about that a little bit later. And bedrock in the same way, and it can be even more critical as you cut it, understanding how it joints or how it's bedded, because that may not only impact the stability of your road prism or of your cut slope, but of the whole prism globally, and upslope and downslope for a large area. So the next, what does that mean for us when we actually build the road? One of the things that we have to think about is how material will behave when we cut it, and then what it's going to do over time. So in the example up above, we have maybe a temporary road with a one-season cut slope, so we can cut it very steeply. Or maybe we have a more permanent road where we need that material to stand at that slope for a longer period of time. Another example, things like till, you can cut till, almost vertically, and it will weather over time, but it'll stand very strong at a very steep slope. Or you could be cutting into a sand that has some water in it, and that of course it's gonna slump right away and go to its and fall to its stable angle right away. And what's important as we're thinking about these things is estimating, not only estimating the materials, but estimating depths and that layering, because we can have things such as a thin veneer of soil over bedrock where we cut through that, and then that thin veneer of soil can retrogress back up. and you're always balancing, especially when you're thinking temporary versus permanent, what to cut that slope at. So in the same example of till, you can cut that very steeply and it will ravel over time, but you're not disturbing a lot of ground, so you're end hauling less, and you'll have less cut slope or less disturbed area that's now going to be subject to mechanical erosion or rainfall, or intercept more area of groundwater. So those are things that you need to understand about material, and then understand about how that impacts your road and the life of your road. In that same way, when you're thinking about temporary versus permanent, you'd be thinking about vegetation and what you can do to slow that erosion. So in the example on the left here, when you're cutting that material at that slope, that is going to ravel continually. So it'll be very difficult to grow anything on that because it's continually raveling. In this case, you obviously have to consider that you're going to fill your ditch up right away. So you have to have an understanding of what it's going to mean over time as your ditch fills. Are you going to be there often enough to maintain that ditch? And if not, what can you do to ensure that's not going to cause an issue? Insloping of roads, swaling the grade so you're not concentrating flow over long periods. And then, of course, on a more permanent road, if you want to get that vegetation started sooner, you're going to cut that back to an angle where it's not going to actively ravel, so that material or that vegetation can get a footing. On the other side, and in the same way, when we're thinking about soil strength or stability. On the fill side, we have to understand the materials that we have so we can understand how they will behave and how strong they are for how much fill we can put down. So in the example above, obviously some finer material, uncompacted fills, probably overly steep versus, likely on approximately the same side slope, a rock fill that's made of non-erodible material that's keyed into a bench. So, and it's not just the overall shape of that, but the permeability or erodibility on the surface, but also understanding where that groundwater level is and how that may also impact your fill slope. So all of these things are a bit broad in the concepts, but how do we fit these into the road design? And that's not my side, that's Matt's.
All right, thanks, Jeremy. Jeremy and I are going to switch back and forth this time, so a little different than our last approach where Jeremy did all his stuff and then I did all my stuff. And of course, I'm going to focus on the software stuff. So we'll start out by talking about assigning subsurface horizons and specifying fill material along your road. And of course, as Aaron said too, I'm going to do this in our software, but hopefully all the concepts that I cover you'll find useful even if you're using other platforms. The user interface and software functionality may differ, but ultimately these considerations are universal. It's not just a reflection of what software you're using. As Jeremy said, we've got our cut slope. If we're in cut, we're going to interact with some subsurface materials. Even if we're not in cut, we're going to be founding our prism on some type of material. So we do want to know what's going on there. And then depending on what we're filling with, will depend how steep we can fill. So we're going to just switch to a quick video here. And we'll go through how we do that in our software. So I'm going to start by just assigning a blanket of material. So in this design that I have pre-set up, my sub-horizon tab is set to our default. And it's set for the entire thing. So right now I don't have any variability for subsurface layers in my design. Okay. So that material that's assigned, the overburden, is my default material. And since that's assigned as the default everywhere, if I change my cut and fill slope angles, that's going to be a global change across the entire design. So we can see that. Now we can add in other materials if we'd like. So I'll just create a new material type called silt. And I can change my cut and fill slope angles to suit whatever I'd like there. Now, when I hit OK this time, nothing changes, and that's because I haven't assigned that material along the length of my road. So I can go to assign by range again, and I can put in the subsurface horizons. I'll start by just assigning two different subsurface layers. I'll give it a deep depth, and I'm going to just hit OK and assign that to my entire road. So dot, dot, to dot, dot is covering everything. So regardless of chainage, what that we start or end at, it's going to cover the whole road. I can go through and I can add different sections to account for changing materials and layer depths along the length of my road here. So I'll go with a veneer of overburden over fractured rock. I'll add that for a 60-meter chunk, and then we'll fast forward, and I've done it for a bunch of ranges. And there we are. So we can see right now that subsurface layer is just an offset of our topo surface. Now we can go more complex than that, and I'll show it here with another example, and that is, well, what if we have something that we need to account for the complexity of having a subsurface horizon that doesn't follow my topo surface? Well, we can build our own tin to reflect the subsurface layer. We'll save that as a train file, and then back in location, we can attach that to our road design. So I've clicked options and add, and I'm adding in a subsurface layer here. So as we can see, we've assigned that. I went into assign by range, and I've when I first connected that subsurface to my road or to my location file, nothing changed. We had to go to assign by range, and instead of assigning a depth offset, we referred to that subsurface terrain file to dictate where we're at. And then we can see here that bedrock layer isn't following my topo surface. My bedrock layer is coming right to my topo, where I've got an existing road prism, and then that fill slope for that road is it's a deeper depth than elsewhere to account for that difference. And then similarly, assigning subhorizons by range, we can assign fill types by range. So here I've got a fill slope that goes further than I'd like, and I'd like to say, okay, rather than just filling with the material that's on site, I want to make sure I fill with a different material. So I'm going to say from station X to station Y, I want to fill with, in this case, I'll use my fractured rock layer. I'll click Add Edit. I'll click OK. We can see our fill slope updates. And then also that material is going to be tracked separately, and we'll talk about that later on. So next we're going to talk about surfacing. For that, I'll pass it back to Jeremy, but just while we have the visual up here, we're just talking about the part of the road that you drive on, and we're talking about the material that you actually put on your subgrade there. So you don't always surface your road. So in the resource sector, usually we're talking about putting gravel down rather than paving. But it does offer benefits, and it's a useful feature to help minimize your environmental impact. I'll let Jeremy take it away from there.
So surfacing probably has one of the larger impacts, or can have one of the larger impacts in the environment, and that's primarily from sediment delivery. But it can even impact things like design speed, or if you have a rough road versus a high-speed road, or one that's full of potholes, that can impact how vehicles interact with the wildlife. So there may be some other things to think about when you're selecting your surfacing. But we have to be careful when we're considering it during the planning and design stages, because we have to think about things like material type. What do we have on hand? Where is it coming from? What is its gradation or depth or permeability? How are we going to compact it? And that's all based on our use and lifespan. So if we catch that stuff at the planning stage, we have more time to and understanding of how we're going to actually flush that out. So for example, in terms of strength and durability, if we have a weaker material that is going to erode or break down to silt versus sand, that's going to change the nature of our road surface significantly over time. In this example, we have some shale that will weather to silt, and so that's going to behave very differently over time than something that is far more coarse grained, such as a granodiorite that will break down to sand. So that's not only creating those fines that maybe cause stability issues in your road prism, or softening of the surface for rutting that can concentrate drainage or cause more dust. It also changes the gradation of that material as it erodes, and the gradation of the material is super important, because that's going to determine how well that material locks together. So in our example here, you can see a poorly graded material is something that has, for example, stuff that's all the same size, or a gap graded material has a bunch of material one size and then a big gap in size and a bunch of material that's a different size. What we're looking for generally in surfacing is a well-graded material something that has a bit of material in each grain size, because that locks together better in a matrix and holds its shape. Ideally, we have angular material, and there's actually a good reference from MOTI, Ministry of Transportation and Infrastructure, that has material gradation charts for a bunch of the materials that will be useful in a road prism. That gradation will also impact how we need to handle it in use. That's compaction, grading, and it'll impact how it handles over time. So in the picture on the left there, we have a poorly graded material where you have a bunch of gravel-sized rock. Now, without the appropriate amount of fines, that gravel is just going to end up on the sides of the road, and that shouldn't be confused with gravel not being a good road surface material. What happens is you have this surplus of larger clasts, and they end up getting pushed to the sides, and all you see on the road surface is maybe a silty or a finer material, and you may want to think that, well, the silt is the best material for my road surface, but that's not what's really going on. What's really going on is the strength of that road prism is that silt that has those clasts or those rocks inside that are making it strong, and the only reason there's a bunch of gravel on the gravel size material on the sides is that there was just an excess of it, and there's not enough fines to lock it together. So what we really want is that material on the left that's well graded. Now, that's going to vary widely depending where you are, right from, you know, being in shot rock to being in swamps. And so you're going to have to find the best balance for cost. But all of that, if we just step back, we just got to remember, because this is what the seminar is about, is how that's going to impact the environment. So on the other side, we want to think about how that is going to put us back into the planning phase. So if you want an overall use, so if you want a fast all season road, you might not have the material for that. So right up front, you're going to want to know that if you can actually build this road, and if there's going to be additional costs. So we can add things like geosynthetics or even additives to the road surfacing when we don't have ideal material, but that all comes at a cost. And if we do a good job planning, we have time to consider that. So that's the basics of surfacing, and we could spend days on it. But I think just for the purposes of this, we'll let Matt talk about how you're going to do this.
All right. So your surfacing and even how your cuts and fills interact with the surrounding terrain are all dependent on how you've set up your cross-section geometry. So in our software, that's controlled in your cross-section template. So here we have a pretty basic anatomy of the road, and Jeremy covered all the parts that we have up here already. But before I go much further, I should speak to how this works in our software. So one of the biggest differences between a geometric design software and a GIS or mapping software is that we're going to consider the road as a surface instead of a line. So to do that, we take a line, so the center line, which is a 3D line with curves on it, and we attach a cross section to it. And as the center lines move, the cross section is going to dynamically update to show the geometry and the behavior that you'd like. That changing and dynamic behavior isn't trivial, so it takes logic to make them behave appropriately. And each cross-section template or template component is like a mini program. Now, attaching the cross-section to your center line and making sure it is smart isn't a big deal for our users. We have the components already pre-built for folks to use. But it is worth being aware of kind of that behavior, that the cross-section is attached to your center line and that it's meant to have smarts in it and update accordingly. So from a user perspective, the templates are a collection of components. Those components are pre-built, available on our eLibrary or in the default templates that come with the software. And if a user wants to deviate from those default cross sections, it's as simple as compiling the components they'd like into a single template and changing the parameters to match the dimensions and behavior they'd like. Yeah, so let's talk about cut and fill slopes. So I talked about assigning those different materials previously. But the image that I just had up was a single subsurface layer that brought in the cuts and fill slopes from our default material. And as you saw last time, if we'd like, we can have the template automatically adjust your cut and fill slope angles to match the assigned material. Now, it's worth noting that you don't have to follow the assigned cut and fill slope angle for those materials. And there's lots of cases where you'll want to deviate from those. It may be that you have a section where you want to deviate from that default material parameter and maybe oversteepen a cut and deal with it from a maintenance standpoint. Or it could be from an operational perspective. So maybe you want to have machine access off your road and you don't want a fill slope angle that's so steep you can't walk equipment up and down off of it. It could also be from a safety perspective. So you may want a recoverable slope where if a driver goes off the road, they're probably not going to flip their vehicle. And it could be from a constructability standpoint. So again, if you have a fill slope and if you plan to build that with a dozer, and if you want to be able to side hill across that slope, well, you can't have it super steep, otherwise you run the risk of rolling your machine. Maybe you go with a reduced cut or fill slope angle just to make it easier to build, which also has the benefits of being easier to revegetate. That premise is worth noting, but usually, at least as a starting point, we still want to consider the way the material is going to behave that we're dealing with. Now, aside from just a simple run-of-the-mill cross-section, we can easily account for other requirements. So this is where I was talking about putting together different components. So these can include things like berms, barriers, walls, and other stability enhancements, such as the cross-section we have here, where we've taken a keyed-in rock fill component and added that in. So, and just worth noting here, these kind of more complex fills, it's always consider what you're dealing with. An important part of that is making sure that you have a solid foundation. Now let's show a quick video on building a cross-section template, and hopefully we don't have the same hiccups. Or at least hopefully I don't have the same hiccups with being able to see the video. So our templates are in the template editor. So we have a library that we can pull from here, and right now I've just got our default templates assigned. So the template itself doesn't have a lot of parameters. We can control our crown and whether volumes are being calculated, but we've got different categories of components. So here I've got a slope component where my cut and fill slope angles are set to auto. As I mentioned, if I want those to be fixed at a set value, I could change that in here to say 1:1, or which is steep, or change it to whatever value I'd like. Our roadway component, so this is where we can control things like surfacing, as Jeremy just introduced. So I can add multiple layers to my surfacing. If I want to eliminate those, I can set the depth to 0. These are going to be tracked separate from my subgrade. So if I just clicked there and it said surface volume 2 for what I clicked on, so that's being tracked as surface volume 2. And of course, we can change our width as well. Now, if I want to build something similar to this, but a little different, I'm just going to copy it, paste it. I'll give it a unique name and identifier, a description and a name. And then I'm going to take components that I don't want out of it and put components that I do want in it. So here we'll create that keyed in rock fill that we previously showed. So I've taken my slopes components. I've got a component here, and it's not showing me much in the view, but it's a fill only component. So I'll change to a different cross section. I can see that, okay, that's doing what I'd like it to do. So that's the one I want. I'll hit copy and I'll paste it up into my new template. And it's coming up in a silly spot. It's also on the wrong side of the road in this case. I'm going to make one that's a template that's asymmetrical. I'll dump it over onto the right, and then I'll remove that on the left. And we can see, okay, that makes no sense. You're not going to build a ditch and then put a keyed-in rock fill on the outside of your ditch. So the draw order matters. So here we've got a little note in there that says add before other components. If we shift it up, we shift it into a fill situation, that's behaving the way I'd like now. So there is a construction order in how these are attached. And then we can change the parameters to suit what we'd like. So here I'll just narrow up that thickness a little bit to be 2 meters thick instead of 2.5. And that is being tracked as surface volume 4. Now I'll hit OK here. And nothing's going to change in my cross section because I haven't assigned that template along a range yet. So here it's that same section that I previously changed. We can go up to assign by range, and instead of changing our fill types, we can change our template. We'll go from station X to station Y. We'll click add edit, and clicking that add edit part is important. Otherwise it won't assign it. And there we are. We'll just click in there so we can see what we're dealing with. Excellent. All right. So the next thing that we have on to talk about that's cross-section related is stripping. We'll talk about clearing when we show this as well. But stripping is really important. So if you think about it as kind of a weakest link in a chain kind of comparison, you can have the best fill material in the world, but if you put that on a weak soil, well, it's only going to perform as well as that weak soil that you're founded on. So to get around that, usually we'll remove a weak soil layer. And oftentimes in new construction, that weak soil layer is going to be in organic soils right on top of your surface. So we'll strip away those organics and make sure we're building on competent, strong material. So we do that to help ensure that that fill slope or fill that we build stays there. And it's going to make sure that we don't have a squishy layer underneath there that could cause rutting and poor performance from our road surface. But it's going to have other impacts too. So it's going to change the volumes that we're tracking. So the stripping layer, you don't want to build with that. You don't want to just pull that off and incorporate it in your fill and have some poor material mixed in with the stuff that you've taken the time to shape into a road. So that's going to be tracked as its own entity. And since we are taking, in this case, a foot off our road while we've effectively dropping down the topo surface. So we'll want to drop down our grade so we can balance that as it was before. Now in the next video here, I'm going to talk about assigning clearing limits as well. We do that in the same part of the software. And that has other benefits. So clearing limits, obviously, we're increasing the footprint of the road, even though we're not going to actually remove all the vegetation. It'll usually just be visual barriers. But clearing it also has benefits. So if we clear that out, we're going to give area to add storage for snow removal. So we can wing back our snow banks in the winter, which provides reduces barriers for wildlife. And then it also increases sunlight on your road, which can be beneficial to dry things out quicker. So you reduce the risk of things like rutting. And even if you're not rutting, there's just less water on the road getting mucked up by tires and producing sediment and being transported to places where we don't like. So we'll quick play on our video here and We'll click Assign by Range. Now, stripping's not in templates, it's in its own area, so site prep. So here I'm going to say we're going to remove 0.3 of a meter. I'm going to assign the outside limits to be slope stakes, so top of cut, bottom of fill, get the whole footprint of a road, and I've added a 30 centimeter offset. And then in the top, I've assigned my clearing, so I'm going with a 30 meter wide clearing. I've also added a 3 meter wide additional width where it's needed. So if I have a big fill or a big cut, it's not just going to keep my 15 meter width on either side, it's going to bump that out an additional 3 meters from my crest or toe. So that's how we assign stripping. And the next thing that we have is daylighting. So it's another cross section specific consideration. And with this, so if you're going through cut on a side slope, it may be a case where you want to have a true through cut with a cut slope on either side of your road. Now, often, if you're close horizontally to the that topo surface, it may make sense to cut out instead of up. Now, there's benefits to this from a safety perspective. It may be that you're removing visual barriers. It may be that it's an easy way to add pullouts. More often than not, if nothing else, it represents it reflects how you're actually going to build it. So it's kind of unusual to leave a little wedge of material there versus just knocking it out of the way. So, and we do want our design to reflect how it's going to be built so we can see all the things that we're going to interact with. So let's look at where daylight lives in the software and how to play with it. It lives in a few places. It's always going to be in the templates, but maybe in multiple templates. So let's pop up to our templates editor. So we can see if we get close to the edge, that daylight is being applied. So how is that controlled? Well, we'll expand our list here. Right now, where it's a through cut, that cut slope angle is coming from our slope, just the same as it was as when the cut slope was on the high side. Here we'll cycle through, and if I pull that over, I can see that's highlighted magenta now. So I know that that's in our ditch component. So we can look here, and I'm not seeing any daylight parameters, but there's this little box, show advanced parameters. And up there we can see that, okay, my daylight distance is set to 5 meters. If I turn that off, or set it to 0, it's the same as turning it off. If I make it 10, the tolerance for when that's actually daylighted increases. Now let's turn that off here. Oh, and we can also change the cut slope and angle of that as well. So it doesn't have to be flat, doesn't have to be at a specific angle. You can set it to be whatever you'd like. So now let's turn that off. And we can see in our roadway component, we have a daylight setting there as well. So daylighting is a common but not universal property in some of our templates. Now, if you want daylighting and you have a template that does, or a template component that doesn't have it, you can go into our links and connectors, and there's a specific daylighting component in there. You can copy that out, paste that in wherever you like. And once again, we can see that where we paste it matters. So it's attached to the outside of my road, whereas if I shift it down, it's attached to the outside of my ditch. So that is daylighting. Now, let's talk about our photos here. So right now, what we're seeing on the right is obviously not ideal. So this is your infinite cut or fill slope, where if we cut at the assigned cut slope angle, it's basically going on forever. They're not constructible. Now, if we go with a less extreme example here, we've got these sliver cuts and fills. So before we address this, we need to just reiterate a big part of why we design is that we want our model to represent what we actually want to build so we can see how it's going to interact with the surrounding terrain, so we can make better decisions and reduce our environmental impact, and so we can communicate those expectations to builders. Now, if you get those sliver cuts or fills or infinite cuts and fills, it's important to ask yourself, how realistic is this? And then as an extension of that, is it constructible? Well, the infinite ones, no. The sliver ones, maybe. As is, probably not. And I say that because, well, maybe you'll require special equipment. So maybe you have to mobilize in an excavator with a long boom to build what you have designed. So that's going to be a cost. Or maybe it's that you need to build a tote road, so a temporary access road to either get to the top of the cut or get to the bottom of the fill to make a foundation to build off of, or just to get within the reach of your machine. So both those options represent a significant cost. And I'm not going to show it, but you can design your tote roads if you'd like. But if you're thinking of going that route, you really do need to ask yourself, does it make sense to absorb those costs? And if you're not willing to, just remember that poorly built cut and fill slopes may fail, which is a safety concern, but it's also an environmental concern, which is why everyone's here. So, and that could be that it's a catastrophic failure causing a landslide going down into a creek, or it could just be raveling material filling in your ditch. Of course, it's probably not going to happen where you expect it. You're no longer controlling where that water is going, and maybe you concentrate flows to somewhere that hasn't seen much flow before, which causes erosion, which feeds into sedimenting a fish creek. Now, this problem isn't an uncommon problem on steep slopes, and perhaps you can mitigate the problem with stability enhancements. So maybe you build a key and rock fill, for example, or to have a steeper fill slope angle. Perhaps you can develop a plan that uses temporary cuts and fill slopes and an appropriate inspection, maintenance, and decommissioning plan. Oftentimes, a very useful solution, though, is to just move your road. And it could be a minor adjustment, or it could be selecting an entirely different route, depending on what you're up against and what makes the most sense. So with that, we covered moving your alignment in the last two webinars. So when I clicked in new alignment, we won't show that in great detail again. Of course, it's an important part of geometric road design, but we've got other things to cover. I will cover some things that we haven't yet, though. So ultimately, your road alignment isn't just a 1 to 30,000 scale consideration like we talked about last time. Where you put your road influences all aspects of your road's life, including how it will interact with the surrounding environment, and considerations that may not directly relate to the environment can influence your environmental impact. So for example, if you had a pullout for driver safety or for operations to allow vehicles to pass without having to wait a long time to get from the previous one, well, that's inherently not an environmental consideration, but it certainly becomes one if you put that pullout in a spot that causes a degradation to a environmental feature. So maybe you've got fill material spilling down into a fish creek or a wetland. Well, what wasn't an environmental thought now is. Similarly, changing one design parameter often makes it necessary to change others. So for example, it's very common to change something like a cut slope angle, ground type, template, or maybe you change your stripping depth and suddenly you realize your alignment's no longer in the best location. And I mentioned that with the stripping, if you remove the material that's not being accounted for in your subgrade, you want to probably drop that down to get a better balanced cuts and fills. So this complexity leaves us with an inherently iterative process where route selection at the planning stage is refined and occasionally changed completely in the design phase. And as I mentioned last time, you can minimize the later by considering more aspects of geometric design early in the planning stage. Now, other alignment considerations that affect the environment are, well, grade's a big one. So grades are inherently a major safety consideration, but can play a large role in influencing a road's environmental impact. So I'm not going to go into more detail on that here, but it does influence your vertical alignment, and it as a result influences your horizontal alignment, where you put your road. Now, grades also have a large impact on environment in terms of influencing an area's drainage and erosion potential. So without getting into drainage specifics, and that's because our next webinar is going to be dedicated to drainage, or without rehashing that intercept, accumulation, and redirect direction of water we introduced in our first webinar in this series, grades influence water velocity. So if we're talking about runoff that's just on your road surface, well, a steeper road is going to move water quicker. It could be on the road surface or it could be in the ditch. And the faster the water is moving, the more erosion potential it has. Now, on steep grades, it's common to surface your road with coarser material for traction, but it's also helps reduce washouts. Now, if we speak to these photos here, I will talk a little bit of drainage just as a precursor to our next example. The photos on the left, we, from our alignment, have created it, and this road I don't think was designed. It was just built, but we redirected flows to somewhere that they shouldn't be. So in our first webinar series, we talked about how you don't want to dump water, usually don't want to dump water off the edge of the switchback. Well, this one's a weird one. It's the switchbacks are stacked right on top of each other, and you can't tell from that aerial view, but they're actually dished. So the big takeaway wasn't in our first webinar wasn't to don't dump water off switchbacks. It's try to preserve those natural flows. And in this case, instead of that water naturally falling away from the ridge, it gets trapped on the roadway. There's poor drainage structures and it's dished together. So a little bit of water that starts at the top of that series of curves doesn't have an opportunity to leave the road, and it ends up creating a lot of water on the road, which washes away your surfacing and puts that material someplace where you don't want it. The image on the right is well planned. It's if we look at it, we can see that in that draw, the alignment is swaled. So in that case, the alignment's acting as a redundancy. So if those structures fail or become overwhelmed, well, you may lose your road at a specific location. It may be a washout, but it's not going to entirely redirect the flow from that draw into an entirely different area. So we'll keep everything right where it's supposed to be. And then another aspect of how the alignment helps us reduce our environmental impact is through minimizing disturbance area, earthworks, material movement, and through all that, minimizing our emissions during construction. Yeah, and if we look at these two images, this is kind of the biggest tool we have in our software for this is the optimizer. So again, it's one of those cases where the environmental goals and economic goals are hand in hand. The less work we do, the less we disturb, are beneficial. So here we have got a little over a kilometer, and by using mathematical optimization to help us figure out the best spot for our alignment, we've reduced our earthworks quantities by almost 7,000 cubic meters, and we've reduced our disturbance area by 0.2 of a hectare. So we'll just take a quick run through the optimizer here. So here, this is the alignment that was designed by hand. We'll just do a vertical optimization on it. So there's the numbers that we're dealing with. I'll just create a new vertical alignment for comparison. And I'm going to just tell the software how frequently I want to sample along a road. I'm going to set a minimum curve length, and that's just so I don't end up with a bunch of little curves back to back. I'm going to set my maximum and minimum grades. set my minimum K value, and I'll apply that through a range. Now in this case, I've got those two switchbacks where I'm going to want a reduced grade on those, so I can assign different range constraints for specific sections. And there's a lot in here to accommodate for your operational constraints. I'm going to keep this fairly simple, but I will add a control point. So other than just minimizing our cuts and fills, we don't want to accidentally end up with a start or end floating up in space. So I'm tying into two existing roads here. I want them to be at the existing elevation. So we'll run that through. We'll tell it to optimize. It'll take a moment to sample, and it'll solve what we're dealing with. And we'll hit OK, and we'll see our 3D view will change here momentarily. Yeah. So we've reduced our earthworks, we've reduced our disturbance area, and yeah, it's the same example as what I showed previously for those 3D screenshots. Now, benching is another alignment consideration, and it semi-frequently gets confused as being primarily a cross-section consideration. So it's not. So here we have, it's not and it is. It's the presence of a cut or fill slope, yes, but it's primarily a function of where we put the alignment. So here we have half bench construction. So often this is your normal cut and fill where we're trying to minimize our longitudinal material movement. So we'll take from the cut portion of our cross section to build the fill portion of our cross section. But there's other instances where you'll use other benching techniques. So here we've got full bench, 3/4 bench, and fill only. And this isn't all inclusive. There's other benching prescriptions that you'll see. Here, that terminology is referring to how much your road is founded on an excavated bench. So in full bench, the entire road's founded on cut. 3/4 bench, well, 3/4 of the road is founded on cut. And then fill only, none of the road is founded on cut. It's a fill only embankment. Now we may have any one of these categories without giving much thought to it when we're designing. So it may just be that we're balancing our longitudinal material movements and going in and out of maybe a through cut to a full fill. But these are also common prescriptions when you're dealing with specialists to mitigate environmental impact. So, and that's primarily dealing with terrain specialists and geotechnical prescriptions. So in this case, if you're dealing with a specialist and they tell you that you need to have your road in full bench construction here, well, that thing that you weren't giving much attention to when you're balancing your cuts and fills, it becomes a control point. And we want to make sure that we follow that prescription. And that prescription isn't a new template, it's moving your alignment. So we'll just look at a quick video here. It's just a function of whether you move in or you move out or you move up or you move down. So if I take that alignment and move it out while we're in fill only, if I pull that in, we're 1/4 bench, half bench, 3/4 bench, and then we'll go to full bench with daylighting, and it may be that you get prescribed full bench without daylighting. So you leave a wedge of material there. And same for moving it up and down. And we won't show the whole thing here. It's pretty straightforward. Now, the last alignment specific topic I'll touch on in this webinar is curves. So in the previous webinar, those of you that watched saw me add and adjust curves. So aside from just assigning the curve as a curve, we also want to make sure we are accommodating for visibility in our design vehicle. So a big factor that relates to your design vehicle and influences your alignment is clearance for vertical curves and accounting for vehicle sweep and off tracking and horizontal curves. So there are specific software packages developed just for this analysis. In ours, we won't do that full analysis in-house, but you can develop a table for automatically widening either the inside or the outside of your curves, depending on the radius and the change angle that you're working with. To account for visibility, it's yeah, there's tools in the software for that as well, but big things you want to consider are sight stopping distance, So that's going to vary by design speed. It influences what curves to use, and it may require you to remove visual obstructions if you need to see a certain distance ahead. And then in line with that, pullouts are important. So oftentimes you want intervisible pullouts, especially if you're dealing with single lane two-way roads without radio control. And again, it's one of those things that's not really an environmental consideration, but it can become one if you put it in a spot that doesn't make sense. And it's going to have an impact on your disturbance area anyway. Now, aside from these general curve considerations, switchbacks usually have design standards that differ from the rest of your road. So it's common to want to reduce your grades through switchbacks. You're probably going to have a tighter minimum radius for your switchbacks, and then elsewhere on your alignment. And one thing that's important is you should give extra care to make sure that you have topographic relief to lose whatever cut or fill depth they've generated as you turn directly into or out of the hill. So this is kind of common knowledge for anyone that's designed a switchback, but if you haven't, just think about it. If you're on one aspect, you turn directly into the hill, well, you're going to increase your cut to stay at your design grade. And then you want to make sure that you have the topographic relief so you actually get out of that cut and you don't just have this big trench going up the hill because you didn't lose that cut. If you have that big trench, it's not going to be ideal. You're going to increase your disturbance areas, construction emissions, and your costs are going to skyrocket, so no one's going to be happy. And with that, I'll pass it back to Jeremy for a bit.
So Matt touched on it really. Didn't share my cam. Matt just touched on it already, but that movement of material or excavation, that probably has the largest impact on the cost of your road. So understanding and planning for that can make a big difference. So we really just need to understand the broad concept of mass haul, material expansion and shrinkage, and where material is coming from or going to, and how or when in the construction process that's going to happen. So understanding these things ahead of construction can help reduce the impact on the environment. For example, knowing when you can or cannot pioneer ahead if you need to move material forward in your design. This could cause damage to things like, wetlands or impact sensitive slopes or slope stability with materials tracking on weak subgrades. But also planning your spoil sites in less sensitive areas. So thinking ahead and understanding that you're going to need places to spoil excess material, understanding the type of material that is and where you can put it. And really just minimizing the material movement by will reduce the road's physical carbon footprint. So again, having that plan and the right specialists involved can really tighten up that process and help with the design. So just a real quick overview of mass haul. So mass haul means material movement along the road. So when ideally we dig, and you saw Matt's cut and fill road prism there, we could cut material out of the cut bank and put it in the fill. That's zero mass haul. So you're not moving that material along the road, you're just moving it side to side. So in the graphic here, you can see the road plan view profile, and then the bottom is the mass haul diagram. A mass haul diagram has two axes. The vertical axis is volume of excavated material, and the horizontal axis is just length along the road. So above the zero line, you're accumulating excess cut material. So if the line is climbing, that means as you go along each meter of road, you're generating more cut material than you have fill. And in the same way, below that line, you have excess fill material. Or you have a deficit of material. So as that line is dropping, that means you need more material. You're not cutting enough for the fill volume that you require. So that zero line is where the material is just moving back and forth. When it curves above the line, as you can see from the arrows are pointing forward along the road. That means as you're generating that cut above the zero line, that material is required further on the road where it's dropping again. So having an understanding of that and whether you can do that or not is super important. Where it's below the line, obviously it's the opposite. You're generating a need for more fill material, but you're not getting that fill material until farther up the road. So that's mass haul in a nutshell, but it's not quite as simple as that, because depending on the material will behave differently and change by state. So now we're talking about expansion versus shrinkage. So the three main states of material are bank, which means the material as it sits in the ground before we've touched it. And then after we touch it and we're moving it, it's in its loose state. I like to use the term fully fluffed because it's what it is when it's in the truck or in the blade of the dozer or the bucket of the excavator, as it's in its largest form. And then in its final form, final or placed, it's when we stick it back into the ground. And that's where we're recompacting it once again. So each material type will act differently depending on what it's made of. So, for example, and not just what it's made of, but how it was formed. So a till, which is super compact, say it's silt or sand. Once you touch it, it's going to fluff up. But once you compact it back down, it's not going to get to the same volume. You just can't compact it enough. In the same way, so maybe it'll end up 5% bigger than it was at the start. Something like a bedrock, it'll be, it comes out of the bank in one volume. You blast it, it's in these big blocky chunks. You throw it in a truck, it's very, very much, and maybe up to a factor of 2, maybe 50 to 80% bigger. And then in its final form, it may be 20 to 50% larger than what it was when you dug it, or before you dug it up. And then, back to the normal ones like sand and gravel, which seem to stay fairly stable. But so understanding all of those things is super important, because it will change your material balance as you move along the road. And the software can actually model this for you.
It can. So before I touch on expansion and shrinkage, we'll just talk about how the mass haul behaves in the software from a really basic sense here. So as Jeremy said, it's all about tracking material surplus and deficits. And so we've got this road, it's largely designed, and my mass haul diagram right now is going up and down. So I've got material moving backwards and forwards. And where that crosses the zero line is where that material balances. So at the zero line, while it's fill from before that is, it's a transition for where we move things. Now, there's material movement categories in here, so free haul, overall, and then end haul. So we can set different distances to represent how we're moving that. So here I've got my free haul distance is set to be fairly short, so maybe representative of an excavator, whereas my overall distance is kind of a medium distance. So that's your long pushes with the dozer. And then anything beyond that is going to be assumed to go into a truck and moved with a truck. Now here, as we adjust this, we can see that if I increase my cut, well, I create a surplus of material, or less of a deficit in this case. And if I'm staying below that zero line, as Jeremy said, our material is assumed to be moved backwards. Now I won't go through this whole thing. We covered our bases pretty good here, but well, how does expansion and compaction or expansion and shrinkage fit into things? Well, it affects how you balance your road, which, okay, well, you may say that's just a design detail. Well, it's not. It's going to decide whether you move your alignment up or down to get that balance to minimize your cuts and fills. So here I've gone into my ground type and I changed that. So I put my cut value of 1 and my fill value of 1.2. So that's that my material's shrinking about 20%. Now, if I change that number for the same material to 0.8, that's a case where that material is getting bigger. So here we'll see that we generated surplus, which, okay, we want to lift the grade up a little bit so we minimize that material movement. Right now we'd have a surplus and we need to dispose of it, which is a waste of effort, a waste of emissions, and it's going to increase our disturbance area. So that mass haul is, if I'm doing a design by hand, I still use it. It's a nice graphic. It's really interactive, but it doesn't fully grasp all the complexity of what's going on. So if you need to account for material quality, and that is to say, if we have a certain material that we need on a certain section, well, it's not good enough to just say, oh, I've got all the material I need. My cut equals my fill. Away we go. Well, it may mean that you may need to consider, well, I need a cut equal to my fill for each material that I'm going to use. So with that, let's take a peek at our video here. And in this example, it's the same example that we started with where I assigned my fill type just as a material. So I'm saying that from station 430 to 510, we need solid rock for my fill. Right now, the mass haul diagram isn't showing me what I'm referring to, and that is it's showing material either going one direction or another. We can use our OptiHaul graphic, which shows us, well, in reality, we've got that solid rock that's coming from back where we have our solid rock source, but that material that we're excavating at that location is going to be used in a fill previous to that. So there is complexity in this stuff. It's sometimes not intuitive. And for that other example where I use that keyed in rock fill template, well, those other layers, be it the surfacing layer or that surfacing layer 4, I can assign those into my materials. So now, instead of just being tracked tabularly as its own entity, that's going to be incorporated in my mass haul diagram. So here I've got two sources. I've got a source for my rock at the start, and I've got a source for my surfacing material kind of midway through. So we can see those spikes in the mass haul diagram representing those sources. But again, the mass haul diagram is not showing us all of the complexity. So here we can see again, we've got material at the same location going in multiple directions. So with that, I'll pass it back to Jeremy and yeah, keep pushing through.
Sorry about that. I didn't hit the buttons quickly enough. So we talked about how we're moving this material. Now we have to think about what we're going to do with it. So to start off here, we'll talk about borrow sites. So borrow sites can be for many things. They can either be for material deficits where you just don't have enough material for your road prism, or they can be for surfacing. Or they can be for things like buttresses, like special construction things. Generally, in borrow sites, the main consideration is for that material quality because you're using it in your road. But for the impacts, we have to consider where that borrow site is located. So how big it is overall, how it can be reclaimed, and how will it impact drainage. Sometimes you need a specific drainage plan for the site. And if it's a borrow and rock, understanding things like metal leaching and acid rock drainage. And depending on the size and complexity, you can decide whether you just need to account for the overall size of that borrow or whether it needs a separate detailed design. And sometimes that design is just the overall shape. And sometimes that design is a construction sequence of how you'll actually exploit that material properly. But again, planning for these things and understanding them ahead of time are going to give you the most opportunity to think about and minimize the impacts of it. On the other side of things, when we have too much material and we need to spoil it. Now, the main consideration, I would say, is stability, and that's the main contributor to that is the material type, the location, and the stability of that area. But you must also consider the construction sequencing, as the material type may change as the road progresses, and it might be important for staging or for construction of the spoil site. Like, for example, you might want to use blast rock in the top picture there. That's a very, very large spoil site, and there's a windrow of riprap. I don't know if you can see it at the toe of one of those big slopes. So understanding when you're going to hit certain materials and staging that spoil site so you can put that spoil in the right place. And on the opposite side of that, maybe you want to save your organics or the grubbing from the ground surface to cap that pile for revegetation or reclamation. But again, on the environmental side, understanding that sediment potential, how big that is, and from the sediment, how that drainage is working, or just its proximity to other sensitive areas. All of those things are important to consider, not just from the engineering cost side, but also from the environmental side. And I kind of spoke to it already on the construction sequencing side. We recall that mass haul diagram, and we're above and below the zero line, whether that material is moving back or forward. That's a really important thing to understand when you're designing these sites. The picture on the screen here is what we refer to as a single heading road. So that ground is steep, and that excavator is excavating the road prism as it goes. And it's so steep, he's even having to end haul the stumps and roots and grubbing material. So it's not possible for him to move forward material on that road simply. So if you have your mass haul is going above the zero line in this kind of ground, that's not an easy thing to do, because you can't just move it forward as you're excavating it. So you'd have to do things like temporarily store it. So you have to understand that beforehand, before designing these spoil sites, of exactly when you can do it. And again, in the same way, staging, if you are going to be staging those things, stage them in a way where if there's useful material that you are going to use later, you're putting that aside into a place where you can still access it. And again, as you get bigger on spoil sites or borrow sites, you might be digging into more detailed design. In that previous slide, that spoil site actually deserved and got a slope stability analysis and a detailed design, because it really mattered where material was going to go. And there were several spoil sites in that particular example where you could move different materials so that you could build them in the way that you want. The other thing to think about when you're having a lot of mass haul is understanding the need for tending those areas and the need for extra machines. So that's something that you're going to want to know up front as you plan for these things. So how that happens in the software is it's not my business, that's Matt's.
Alrighty. All right, so before I jump right in to pick up where Jeremy left off, we'll backtrack a little bit to talk about the actual spoil and borrow site design. So everything I've shown today has been in location. Now, location works by having a center line with a cross-section geometry attached to it. So, and before I go on here, I should say that you can include your borrow sites as a linear feature. It could be that you're mining your ditch for subgrade material, for example. Or it could be that your spoil site is a linear feature. And so in that case, we're side casting material. Now, side casting, I'll just say it's one of those things that may work in some instances, but it can cause terrain stability issues in others. So that's the same with anything. Be careful when you use it. But I won't show that today. I'm on our next webinar, I'm going to show something that kind of alludes to a useful way to account for that, but it'll be in a drainage application. So the remaining types of borrow and spoil are those bulk excavations and bulk fills. So these aren't easily or not well represented by just a center line with an alignment attached or a cross section attached to them. So we're going to do that in a different module of the software. So we'll do that in Train. Before we show that, and as Jeremy mentioned too, like these can vary wildly in complexity. So here I'm going to show a really simple spoil design where we're going to take into account volumes and take into account spatially, but I won't get into the designing drainage and stuff like that, but you absolutely can if you'd like. And then borrow sites similarly, you can deal with a bunch of complexity. And here on the right, it's a aggregate mine, so it's a proper mine, but the concept is still the same. A mine is just a big borrow site where you're pulling material from the earth. So you, as Jeremy said, you can get really complex and talk about staging different phases and kind of have your whole design as have a time component in it where you're looking at, okay, phase 1, phase 2, phase 3. You can do that. The requirements of your project will dictate whether or not that complexity is appropriate. All right, so now we're good for the video. So we'll go through a quick spoil site design. So here I'm going to just start out in location, and I'm starting out in location. I'm going to take a quick glance around and look for an area where I suspect is going to be stable, and I'm not going to interfere with a bunch of drainage concerns. So looks like a good spot there. Also going to just check, okay, how much bore and waste am I anticipating here? So that comes from my mass haul diagram or a data table. And then I'm going to go over into the terrain module and I'm going to actually design it. So here I've got my topo surface in as a background. I'm going to draw in a top of spoil feature. I'm going to use a version 10 feature here, which will automatically adjust that up or down to get the volume I'd like to store there. And in previous versions, you can do that iteratively, just adjust it up and down until you get the volume you'd like. So here I'm still just drawing in that top. I kind of did it a funny way. Could have just doodled it in by hand. Join that feature. There's direction for this feature, so I want to grade to the outside. So I'll click terrain modeling and then check the grading, and I want to grade to the right side, the outside. I'm going to set my fill slope angle and cut slope angle to be 1.5 to 1 in this case. I'm going to set the slope line spacing to be 2 meters, and I'm going to tell it that volume required is equal to the volume that my designs told me. And in reality, it probably makes sense to leave yourself some wiggle room there to design it larger so you have more room if you need it. But there, we've got that. We've got a 3D design of our surface. And yeah, can't emphasize it enough. You can go into as much complexity as you'd like here. You can have different surfaces. You could bench that out, plan your drainage, have a rock barrier there at the toe. Yeah, lots of flexibility. We're keeping it simple though for the sake of time. Now let's talk about that movement direction constraint. So this is one of the things Jeremy just talked about. It's a fairly common thing to be overlooked. We'll start with a flat example and we'll talk about it in a steep example. So here we have a design. The vertical scale on my profile is super exaggerated here, so we're only going up and down a few meters, but there's a series of wetlands. So right now we can see that mass haul diagram. I've got a deficit between 15 and 20,000 cubic meters. So we need to get that material from somewhere. So we can go in and we can assign our pit locations. And we could assign, I'll start by adding one at the start. So here I'm going to tell it what material I'd like. In this case, the pit's not actually right at the start of my road, so I'm going to add a dead haul distance in it. So the pit is actually 5 kilometers away in this case. We can add in more. And I'm using smart pits here, where I'm going to tell the software to solve for which pits to use based on costs. Now, without accounting for my movement constraint, well, it tells me to use these pits. Okay, well, that doesn't actually work. We've got wetlands that we have to, or bogs in this case, that we need to cross. So you can't just magically get a piece of equipment to the other end to move that material backwards, as we're showing here. So right now, what we have designed is the cheapest solution, but it's pretty deceiving because that cheapest solution isn't implementable. So in reality, when you go to do this, you're setting up your contractor to be under the gun. They think that they can move this X amount of material so far. It doesn't work. Maybe they are not making the best decisions and they try to just go for it. They'll try and walk equipment across, cause damage to the bog. Maybe they get stuck, which is going to cause more damage to the bog, but also have them there longer. Maybe they're fueling now in the bog now to try and get out. So let's take this and we'll add a forward movement direction constraint. So here we need to build to that pit in order to use it. So we'll apply that, we'll hit recalculate. And we'll see that with that forward direction constraint, as we talked about before, that forward movement, all our material movement is above the 0 line. And yes, it's going to cost more, but at least we have a plan that's going to work. Whereas that cheaper solution before, it's still going to cost more. It's just that you're going to go into it thinking that it's going to cost less. And if we just do a quick comparison here, even if you're not focused on the costs, we can see that it has a real impact. We're going from the average haul distance of being under 300 meters to over a kilometer. So that's that. Now, this isn't just a flat, swampy ground consideration. And as the example Jeremy had, it's a very real steep consideration as well. So we'll play this through. Here we've got a design with a big through cut right off the start. And it's kind of one of those things that it's inevitable. In order to get through there, we have to go through a lot of cut. Now, after that, we're crossing some pretty rugged terrain, steep, rocky terrain. And as designed right now, just looking at the mass haul diagram, we can say, okay, that doesn't make any sense. Because we've got a forward material movement on really steep side slopes. And as Jeremy said, you could stage that, or maybe you open up access with a tote road, but oftentimes it just adds unnecessary complexity when you could consider that in the design phase and avoid it. So here, if we add in a backwards movement constraint, we already had a spoil site assigned. So that material gets moved backwards, and I'm just going to re-optimize my alignment. And it affects our alignment. So we've got that through cuts moved back, and then there's no longer a surplus of material to deal with to move ahead. So what we've done is we've shifted the alignment down to minimize our cuts and fills. So I think that's it for me.
Awesome. Well, hey, thanks. Thank you, Matt. Thank you, Jeremy. So up next, I just wanted to highlight what's coming up in our webinar series. So in 2 weeks from now, we are going to be putting on part 4 or episode 4 of the series. So the last official one, and that's all focused on drainage elements. following that, the unofficial part 5, which is all about how to communicate that road design. So if you haven't done so already, I encourage you all, go up to, I think it's on our softtree.com/webinars, totally free to register, like you know right now. And I hope you can join us for it. With that, we are going to move over into our Q&A section. Jeremy, would you like to get your camera showing as well? Because the first question is coming to you. Awesome. So Jeremy, do you have any go-to strategies for areas with poor soil bearing capacity, such as bogs and wetlands? For example, instances where you don't want to strip.
Right, so we hit that relatively often, and that can be, things like what Matt was talking about, like a bog where you have deep, weak soils with a high water table, or we've run into it in the north where there's shallow ice-rich permafrost. And depending on lifespan, we have things like geotextiles or geogrids that you can put down first and then put your fill over top of, or for more temporary, or if you're in the water table, you can put down wood. So for example, in the north, where we don't want to disturb the ground surface at all, you'll actually go in and hand fall and hand trim all of that woody debris, get it on the ground, and then you can put another good mix is geogrid with non-woven geotextile, so you got some strength and then some filtration, so you're not getting materials migrating up or down, and then put your fill on top of that. On the coast here, we will often use just wood in wet areas, because once we lay that down and put our road ballast or road surfacing on top, that material will always be underwater. So even if you have a more permanent road, if you get that wood underneath the water table, it generally goes anaerobic and it won't rot. And then you can even use wood in a more permanent road if you're under that water table.
Awesome. Thank you for that great answer, Jeremy. Matt, I'm going to pass you the next question. So you were talking about rock fills, and are you able to design a wall that can handle things like lock blocks in the software?
Yep. I'll share my screen just quickly.
Oh, sure.
Just a sec.
While he's getting his screen up, I'm going to tackle 2 administrative questions. So apparently I showed a slide that had the wrong date for our next webinar. It's 2 weeks from today. I think it's on March the 10th. Whatever your LinkedIn, or not LinkedIn, go to webinar meeting receipt says. So thank you for catching that typo in our PowerPoint. So yeah, March the 10th is the next one. And then the other question is the link to the recording. Yes, it'll be up on YouTube as fast as we can get someone here at SoftTree to edit it up and put it up there. So within the next day or so. Okay, Matt, it's all yours.
All right. So the answer for lock blocks and other retaining wall structures, yes, we can. There's a folder in the e-library just for walls and barriers. Keep it simple. Oftentimes these kind of engineered structures will require a bit more consideration, and you may use other parts of the software as well. So for example, I mentioned designing a tote road. Well, that may be that if your road's climbing and you want to have lock block wall attached to it, well, maybe you want the toe of that set at a set elevation. So you may design the tote road first and use that as your bench to build up off of. So absolutely yes, and there's lots of other tools to deal with that as well.
Okay, let's tackle a couple more here. Jeremy, I'm going to give you the next one. It says, how are you approaching the metal leaching and acid rock assessment of rock fill and bedrock? Oh, hang on, I got to expand this out to get the full question. Assessment of rock fill and bedrock cuts.
Well, we find that it, in my area of practice anyways, the consideration varies significantly by region and approving authority. There we have places where nobody pays attention to it very much at all, or areas where every time you do a rock cut, you need to test. So generally how that starts is just grab samples on the road, on the ground surface, and the geologists generally take care of that. And so you could take grab samples, just chip them off and send them in for testing. And then that gives you kind of your first pass or of whether you think you're going to have an issue. On the mining side, that's often followed up by a drilling program. And so, and because there's a bit of a history here in BC of there being issues with that. And so certainly on the mining side, it's more of a focus. But yeah, it starts with just surface rock sampling, getting the testing done, and then generally some sort of a drill program if you are going to be excavating over 2 or 3 meters of depth. But that's where your specialist comes in. We certainly default to the geologist for that.
Awesome. And I think we're going to tackle one more question, and I'm going to let each of you have a chance to answer it. So yes, last question of the webinar. What's the mapping software that you use, and which one would you recommend? Let Jeremy start.
Well, I'm an engineer, so I don't actually do anything. Just pointing fingers. We like to use a mix. So in the field, we still use Avenza with just PDF maps, and we make those from a variety of areas, from ArcGIS, from Google Earth, and actually from RoadEng. So most of our stuff is done on the technical side, so it's done in C3D, AutoCAD, or RoadEng, although ArcGIS is an important tool on the planning side.
Awesome. And then Matt, I know you're kind of in software land now, but you used to be out in industry. Do you want to stab at this question as well?
My answer is very much in line with Jeremy's. Really depends what you're doing. So like in that technical engineering space, it's looking at things at a landscape level isn't, well, it can be a requirement, but oftentimes you're using your mapping software just to summarize what you've looked at in a very detailed level. Mapping World used ArcGIS. It works well. I've also used QGIS. The latter versions of QGIS are quite impressive for being a free open source software. But yeah, it's not something that I'm an expert in. I'm an expert in the road design software.
Can I just take one more stab at that? So the one thing that I've been using lately more is where you export your designs directly out of RoadEng, and we carry around a little Trimble R1. It's a Bluetooth GPS unit that uses GLONASS and other things, so it can give you sub-meter accuracy. And we found in the timber, it actually gives even better accuracy than, say, an RTK. And with that, and having the actual plan view of the road, you can see exactly where you are on the road surface as you're walking around. And that is super handy because with the onset of LiDAR, we often do our initial design before we even go into the field. So we'll do that initial alignment in LiDAR and then make PDFs, stick them onto our iPads, and then get out in the field and actually ground truth where you can see meter by meter where you are on the road design, put comments back on, and those comments actually export right back into RoadEng when you get back to the office, and you can bring them up in the background and adjust your alignment based on that. It's a super handy tool, and it took small companies like us from just being able to do small jobs to be able to do 200 and 300 meter long infrastructure projects.
Awesome. I hate to do this. We're going to do one more question because this individual typed you a paragraph, Jeremy. So apologies if I read this terribly. It says, Jeremy, my understanding is that when embankment is constructed on peatlands, they can include 1, constructing the embankment directly on top of the existing peat, 2, excavation of peat and replacement with a more suitable base and sub-base materials, and 3, geosynthetic reinforcement of the embankment on the peat. So the question from this is, which strategy do you recommend based on the height of the peat, traffic, season, or hauling distance?
Yeah, all of those things need to be considered. So that also has, the other thing in there is footprint. So, and then where it is. So if you're in the north, or you're in a place where, or your fill material is finer grained and going to be more sensitive to temperature, and it pushes your fill slopes to a lower extent, that is going to reduce the depth that you will, of the peat or bog, that you will still overland on. The other thing is understanding what's underneath that, because sometimes it's not just excavating that weak layer, but once you open up the layer below, you're getting into more trouble. So then the other piece is, even if you've got a long haul distance and you think you can reduce the haul by excavating and replacing, you have to consider now you're hauling that material away. So I would say, rule of thumb, if something is 1 meter deep and you think you can cut it without having a huge problem with water or getting rid of that material, it can usually a bit of a no-brainer to just get that out of there and put your material right down on something underneath. Because as soon as you're overlanding, if that peat is really weak, you're adding the cost of the geosynthetic, geogrid, or whatever material you're putting underneath. And you also may have to have a bit better quality material because it has to be stable on top and spread load on that weak layer. So that's a tough question to answer because there's so many things that are going to affect it. But if you're up in that 2 to 3 meter depth, you're going to have a hard time. You're going to have a hard time excavating and replacing, because if you don't bring your fill up above the ground around, you're going to have all sorts of troubles, and sort of you've probably just increased the overall quantity of structural fill you require.
Maybe we'll have to add a 5th or 6th webinar, I should say, on this one. Bring you back for one more, Jeremy. Awesome. Well, I'm actually going to cut it there. We are 14 minutes over time, so thank you all for spending a couple hours with us today, talking about geometric road design and how you can use it to reduce the environmental impact of your road. Please do make sure to check out episode 4, drainage, running 2 weeks today, same time, different login link. So thank you, everyone. Thanks, Jeremy. Thanks, Matt. And thank you, Brian.
Thanks, everyone.
Bye, everyone.